Okay class, so here is the explanation video for this initial rate laws problem. And this is a really sort of classic problem, pretty standard I would say. And this one's a little bit more complicated because we've got sort of a lot of data and I've got 3 different reagents in my problem. So always the first thing I'm going to do is write the general form of the rate law for this reaction. And this is just going to be R, the rate of the reaction equals K times the concentration of our different starting materials raised to some power. That is the power that the order that we're going to be solving for. So this is the first step. This is always the first step, writing out the general form of the rate law. Here I've got my concentration of H2SeO3 raised to X, H plus raised to Y, I minus raised to Z. And I want to point out, just so that we're, if you're following along, if you've done this before, the order in the problem is different than the order that we're seeing here. And I've sort of followed the order here, H2SeO3, H plus, I minus, which is slightly different than what we see here. It doesn't really matter what the order is, but just want to illustrate that so you don't get confused, just in case you're following along with your own work. Okay, so the first thing we want to do is we want to find our x value. We can only do one thing at a time, and the first thing I'm going to try to do is to figure out what this x value is. So in order to find the value of x, which we would call the order of H2SeO3, what we're going to do is we're going to compare reactions 1 and 2. Okay, and I know that I'm going to compare reactions 1 and 2 because if I look at reactions 1 and 2, what I'm looking for is I only want one of these concentrations to change. So here I'm going from 1.23 times 10 to the minus 4 molar to 2.46 times 10 to the minus 4. So this concentration has doubled, and my other initial concentrations have stayed exactly the same, right? 2.08, 2.08, 3.89, 3.89. So these concentrations are the same. This one has doubled. So any change that I observe in my initial rate, that has to be due to this doubling of my H2SeO3 concentration. So any change that I see here will manifest in a change in my initial rate. So that's how I'm going to use that information to solve for this x value. So I might write the concentration of H2SeO3 doubles, and the rate doubles as well. So I'm saying that the rate doubles when I double the concentration. So here I'm just sort of comparing these two values. So here this doubles, I can just take 2.46 times 10 to the minus 4 divided by this value should equal 2. Same thing here. If I take 1.06 times 10 to the minus 6, I divide that by 5.3 times 10 to the minus 7th. That equals 2. That represents a doubling of that rate. So now we need to sort of say, okay, I've got this information. How does that help me? How do I put that all together? So let's go back to our initial rate law. And what I'm trying to illustrate here now, so Z, is that some of this stuff is going to be constant. So in this case, because my concentration of H plus and my concentration of I minus are not changing, right? Looking at my experiment 1 values, experiment 2 values, these are all going to be constant. Same with my K value, this is going to be constant as well. So we know that the change in my concentration of H2SeO3, that's what caused the change in the rate, right? R represents my rate of my reaction. So I know that a doubling here caused a doubling in my R value. So the way that I sort of set this up and solve for it is I might say, well, if I double my concentration here, so I'm just going to say multiply by 2, that resulted in a doubling of my rate, right? So my rate increased by a factor of 2. This concentration increased by a factor of 2. Now I solve for x, we can see x is equal to 1. So that's the procedure that you need to do for each one of these x, y, and z values. Figure out which experiment only has one thing changing, and then utilize that information to solve for the order. And we need to do that for every single one of these. So the next step would be to find the order in Y. I want to find two experiments where the only thing that's changing is my concentration of H+. So if I look at this data, I notice that experiments 3 and experiments 4, my H2SiO3 concentration stays the same, my I- concentration stays the same. The only thing that's changing is my H+ concentration. I can see again that it's doubling. So I'm doubling my concentration of H+, and then I'm going to see some, change in my initial rate. So I've went ahead and filled out basically the rest of this information. So let's focus in on this bottom part here real quick. So to find Y, order in H+, I'm going to compare reactions 3 and 4, just like I said earlier. 3 and 4, the only thing that's changing is my H+ concentration. So when I change that H+ concentration, when I double it, the rate quadruples. So I'm taking 2.54 times 10 to the minus 5th, divide that by 6.36 times 10 to the minus 6th, I get 3.99. So essentially quadrupling a factor of 4. That factor of 4, that's what I'm going to be putting in as my R value. So R equals 4, then 2 to the Y power, solving for Y gives me an order of 2. So obviously the change in my concentration of H+, doubling that concentration, caused a greater increase in the rate of the reaction, and that's what we're seeing here. For the last part, I'm going to do, again, the same process. Find the order of Z. I'm going to compare reactions 4 and 5. So in this case, reaction number 6 we didn't use at all, and that's totally fine. We don't necessarily need to, but just was an extra experiment that we didn't need to utilize. So compare reactions 4 and 5. The I- concentration doubles, and the rate increases by a factor of 8. It increases 8 times. So sort of looking how I got that value, 2.04 divided by 2.54 times 10 to the minus 5th, that gives me a factor of 8. So if the rate increases by 8 times, 8 is going to be what I put in for my R value, equals 2 to the Z. That will allow me to solve for Z value equals 3, so third order in I-. Then the very last step is just putting this back into my rate equation. So here I've got my full rate equation, R equals K times the concentration of H2SiO3 to the first power, H+ to the second power, I- to the third power. This would be called sixth order overall, which is really improbable and unlikely. But this is just for, the problem itself. Now I'm also going to solve for my K value. And the way that I'm going to solve for my K value is I'm going to choose any experiment that I want. I always just choose experiment number 1 and then plug all of the values in. So we've got initial concentration here, initial concentration of H+, initial concentration of I-, and we've got an initial rate. So we can solve for that K value. This is the value that you should come up with. And then I've also included my units, and I want to include those units just so that the units on R end up being molarity per second. All right, that's that problem. It's a good one.